You're listening to DTFHN for July 15, 2026. I'm your forensically reassembled host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who mass centralize trust in a registry argue about trust. Today's a day where old lessons sit patiently waiting to be relearned by people too clever to check. Let's get into it. And use a 190 dies for one. Silicon Graphics and Apple loaned nearly $4 million in today's money worth of hardware to a movie set. Not as props, as functioning computers. Every screen in the Jurassic Park control room was real, running real software, fed by a team of 4 graphics engineers in a makeshift room next door, responding to radio cues from the set. Let's pull this thread. This was the same year SGI went public. The same year their workstations were rendering Terminator 2 and building the visual effects pipeline that would define Hollywood for a decade. And here they are, putting an iris crimson on a fictional engineer's floor. A machine so large it wouldn't fit on a desk. Running a flighty chess game is set dressing. The R4000 Indigo on Ray Arnold's desk. Barely visible in 2 shots. Blink and you miss it. But it was there, and it was real. Because in 1993, audiences knew what computers looked like. Fabian Sumlaud's deep dive catalogs every machine in the film with the precision of an archaeologist. The Apple PowerBook 100 in Grant's trailer. Motorola Lucembets Hexembenhertz Passamatriga LCD, the kind of screen that made you question your career choices. Dennis Nedry's desk, indescribable mice of 3 machines, 3 monitors, a PDA, and storage devices scattered like evidence at a crime scene. The sinking machine CM5 in the background. The actual supercomputer Nedry references when he says Hammond won't find anyone who can network 8 connection machines. The source code visible on Nedry's screen? Real classic Mac OS API calls. Example code shipped with the Macintosh Developer Toolkit. Somebody on that crew grabbed sample code from Apple's SDK and put it on screen because it looked right, because it was right. Here is what is worth sitting with. Every piece of technology in that control room was available, purchasable, documentable. The SGI workstations ran RISC, a Unix variant. The networking concepts were real. The file system navigator Lex uses later in the film. That was an actual SGI demo application called FSN File System Navigator that shipped with the operating system. A 13-year-old saying, "This is a Unix system, I know this," was not a Hollywood gaffe. It was accurate. One reader in the comments said they were 5 years old when they saw this movie, and now they work in tech. That is not a coincidence. That is what happens when you put real tools on screen. When the technology is genuine, it teaches even when it is pretending to be entertainment. The blueprints were visible. Anybody could follow them. Spielberg spent $875,000 on SGI hardware for a set. SGI got a generation of engineers who wanted to touch those machines. The tools were real. The access was real. And 33 years later, someone is still cataloging every serial number. What happens when technology is designed not to impress you, but to protect you? Story 2. Why does a button like this need to exist? After all, anyone can close a browser tab. Anyone can hit the back button. Anyone can clear their history manually. The argument writes itself. This is a feel-good design pattern, a checkbox for institutional empathy, a way for organizations to signal that they care without changing anything structural. A reasonable person could look at a quick escape button and call it theater. That argument collapses the moment you talk to someone who has actually needed one. The question nobody in the design community wants to sit with is this. What does it mean that we have an established, documented, cross-government web standard for helping people hide the fact that they sought help? The UK's Government Digital Service has formalised it. New Zealand deploys a system called Shielded Site across government and private websites alike. The Vancouver Police Department's implementation opens Google in the same tab and scrubs itself from browser history. These are not edge cases. These are patterns maintained by design systems teams, tested against accessibility standards, refined over years. One developer in the comments mentioned they have built these buttons for multiple organizations and spent significant time thinking through the limitations. What happens with browser prefetch, with session storage, with the back-forward cache? The technical depth is real. This is not a marketing gimmick bolted onto a homepage. This is engineering for a threat model where the adversary is in the same room as the user, where loading the wrong page is evidence, where a browser history entry is a detonator. And the implementations are open. The UK's design system is public. Shielded Site publishes its approach. The code is NAFTA. Site is an approach. The code is inspectable, forkable, improvable. That matters because the organizations that need this pattern most. Small domestic violence shelters, community legal aid clinics, crisis hotlines running on volunteer labor cannot afford to build it from scratch. Open implementation means a 20-person nonprofit gets the same protection engineering as a national government. Every year, these patterns get more sophisticated. Better history clearing, smarter fallback URLs, keyboard shortcuts that do not require a visible click. Engineers are quietly building escape routes into the architecture of the web itself. The button is small, what it represents is not. Someone somewhere is going to click it tonight and the page will vanish and they will be safe for another few minutes. That is what infrastructure is for. 3 stories in, and we're already covering infrastructure that saves lives. Now, let's talk about infrastructure that fits in your pocket. A standard 27 billion parameter model stores each weight as a 16-bit floating point number. 16 bits times 27 billion gives you roughly 54 gigabytes. That is more memory than most laptops have, let alone a phone. The conventional trick is quantization. Round those 16-bit values down to 4 bits, and you get about 18 gigabytes. Better, but still too large for mobile hardware. PrismML asked a different question. What if a weight didn't need to be a number at all? What if it could be a sign? Their U-bit Bonsai 27B stores each weight as either -1 or +1, a single bit per parameter plus a small floating point scale factor shared across groups. The effective precision works out to 1.125 bits per weight. The entire model, 27 billion parameters of reasoning, tool calling, vision, the works. Fits in 3.9 gigabytes? That is smaller than a full precision 2 billion parameter model. Read that again. A model with more than 10 times the parameters packed into less space because the representation is that much more efficient. And it is not a toy. Across 15 benchmarks covering math, coding, instruction following, and vision, the 1-bit variant retains 90% of the full precision baseline's performance. Math and coding barely budge. The ternary variant, which uses -10 and +1 at 5.9 gigabytes, holds on to 95%. For comparison, the best conventional low-bit quantization of the same base model scores lower while burning 2.5 times the memory. Pull this thread and you reach something genuinely new. The constraint on local AI has never been intelligence. Blades exist, the architectures work, the constraint has been footprint. PrismML is compressing the intelligence itself into a form factor that fits where people actually compute. A phone, a Chromebook, an air-gapped clinic laptop with 8 gigs of RAM. This is Apache 2000 licensed, full 262K context window, multimodal with a compact vision tower. Speculative decoding support for speed. The models are on Hugging Face right now. Reports from the Hacker News thread show people already benchmarking it. 9 tokens per second on a Ryzen desktop CPU, no GPU required. The engineering here deserves specific admiration. Training a model to maintain coherent multi-step reasoning when every single weight in the network has been collapsed to a binary sign is not obvious. It should not work as well as it does. The fact that it does, and that Apple is reportedly already in talks with PrismML, tells you where inference is heading. Not to the cloud, not to $1,000 GPU cards, to the device in your pocket, running a model whose weights are ones and zeros, thinking locally, answering locally, with nobody's API key required. The tools exist. They fit in 4 gigabytes. Go get them. We talked about trust earlier, who you trust with your network. Tailscale just learned that lesson the hard way. The fix is 6 words long. Tailscale SSH now rejects usernames with leading dashes. 6 words to close a privilege escalation bug that handed out root access. And the mechanism is so old it has its own Wikipedia page. Tailscale's SSH feature, which replaces OpenSSH with their own handler running inside the mesh. Pass usernames directly as arguments to GET, a command line utility for looking up system accounts. If you handed it a username starting with a dash, GET didn't see a username, it saw a flag, and depending on which flags you strung together, you could convince the system you were someone you weren't. Someone like root. This is argument injection. It predates the web. It predates Linux. One of the Hacker News commenters traces it back to AIX3, which shipped in 1990. 36 years ago, engineers learned that you do not pass untrusted strings as command line arguments to subport sources without sanitizing them first. And here we are in 2026, learning it again. The deeper lesson is architectural. Another commenter nails it. Why call Getent as a subprocess at all when getPonem exists as a direct system call? The answer, almost certainly, is convenience. Shelling out to a command is 5 lines of code. Binding to the POSIX API properly is 20. And those 15 lines of difference are exactly where the root shell lives. Now run the open-close test on this. Tailscale is a proprietary mesh network. The client has open-source components, but the coordination server, the thing that decides who connects to what, is closed. When their SSH implementation has a bug this fundamental, you can read the advisory, but you cannot read the code path that produced it. You cannot audit the fix. You have to trust the 6-word summary. A pure WireGuard setup with OpenSSH, which several commenters point out they prefer, gives you decades of hardened auditable code where the argument parsing has been fuzzed by every security researcher with a free afternoon. The comedy here is quiet. Tailscale built a beautiful product that simplifies networking for thousands of teams. And the thing that tripped them up wasn't some exotic cryptographic side channel. It wasn't a 0 day in the WireGuard protocol. It was a dash. A single leading dash in a username field, exploiting a pattern so well documented it belongs in a museum. The convenience that made their SSH feature attractive. Fewer moving parts, tighter integration, less configuration. is the same convenience that skipped the system call and shelled out to a subprocess instead. The tools to prevent this have existed for decades. They just weren't used. Moving on. One commenter on this piece admits something refreshingly honest. They've never quite understood how RPKI actually prevents root hijacks. And that confusion is worth sitting with, because it reveals something beautiful about how the system actually works. Think of it like a medieval wax seal. A king presses his signet ring into hot wax on a letter. The seal doesn't prevent forgery. It doesn't stop someone from writing a fake decree. What it does is give every recipient a way to check whether the letter is genuine. RPKI works the same way. It doesn't prevent a rogue network from announcing a prefix it doesn't own. It gives every router downstream the ability to verify the announcement and throw it away if the signature doesn't match. Now the 5 regional intranet registries operate the root of that trust chain. They're the signet rings. And for most of the intranet, publishing your route origin authorizations through the RAS is perfectly fine. Which makes the question this research asks genuinely interesting. Who are the people running their own tiny publication servers? And why would they bother? The researchers found a long tail of independent operators, ISPs, cloud providers, universities, hobbyists, RPKIAS companies. The distribution is wildly skewed. A handful of large players publish most ROAs. And then there's this archipelago of small servers, each announcing fewer than 1,300 objects. The craft here deserves attention. Running your own RPKI publication point means maintaining certificates, keeping repositories available for relying parties to sync, and doing it reliably enough that your roots don't get dropped by validators worldwide. It's infrastructure work with zero glory and real consequences if you get it wrong. And yet people do it. They do it for operational independence, for faster update cycles, for the same reason people run their own DNS authoritative servers instead of parking everything behind a provider. Control over your own cryptographic assertions about your own address space. That's not paranoia. That's engineering hygiene. The whole architecture is open. The standards are public RFCs. The validation software is open source. Anyone with address space and the will to learn can participate in securing the routing layer of the internet. No vendor lock-in, no permission required. This is infrastructure as a public good, maintained by people who care enough to run one more server they'll never get thanked for. Moving on. When does an architecture stop being alternative and start being inevitable? Because there's a pattern in computing where the open option spends a decade being dismissed as a toy, then another 5 years being grudgingly acknowledged. And then one morning, the industry wakes up and pretends it was obvious all along. Linux followed that arc. So did TCP/IP. And now RISC-V is entering what might be its pretending it was obvious phase. At the RISC-V Summit, Europe in Bologna, Kriste Asanovic declared the State of the Union strong and pointed to something the embedded-only skeptics need to reckon with. Server-class silicon is arriving. Real chips, not roadmaps. The RVA-23 standard, ratified in October 2024, gives hardware and software teams a shared target for the first time at the enterprise level. Developers can test on actual hardware instead of emulators. That's the difference between a science project and a platform. And the names backing this aren't startups hoping for acqui-hires. Qualcomm, NVIDIA, Meta, Google, Alibaba. These companies aren't investing in RISC-V because they love openness. They're investing because they are tired of paying rent. Every dollar sent to a proprietary ISA licenser is a dollar that doesn't go into differentiation. RISC-V lets you build exactly the silicon you need without asking permission or writing a check to someone else's IP portfolio. Here's the detail that caught my attention. Asinovich introduced something called optimization guidance options. Flags like oils and volt that don't just describe what an instruction does, but how fast it should execute. Previous RISC-V specs left performance ambiguous, which meant some implementations handled misaligned memory accesses through slow trap and emulate hacks. The new guidance essentially tells hardware vendors, if your silicon can't do this at speed, software will route around you. That's a maturity signal. You don't write performance contracts for toy architectures. One commenter noted the embedded market has already tipped. Espressif and others have made RISC faculty in default for new microcontrollers. The data center is the next domino. And the beautiful thing about an open ISA is that the blueprint belongs to everyone. 1,000 teams building freely. No gatekeepers standing on the ladder. The architecture is the commons. The innovation happens on top. Earlier we talked about formal verification changing the game. Story 7 takes that energy somewhere delightful. Combinatorial game theory, formalized in Lean. So real numbers have a field structure. They contain the real numbers, the ordinal numbers, infinitesimals, and things like the square root of omega. John Conway invented them in 1976 by studying games where two players take turns, moving until one of them can't. The entire number system falls out of the game theory, not the other way around. Someone is now proving all of this correct, line by line, in a theorem proverb. The project is called Combinatorial Games in Lean, and it's exactly what it sounds like. A formalization in Lean 4 of the mathematics behind two-player perfect information games. The kind where there's no randomness, no hidden state, no draws. You move or you lose. Nim, Hackenbush, Chomp. The repository aims to build up from general game theory through numbers and surreal numbers, establishing their algebraic properties with machine-checked proofs. Here's a devil's advocate angle. Why bother? Conway's on numbers in games has been around for decades. Mathematicians trust it. Students learn from it. The proofs work. What does running them through a proof assistant actually buy you? It buys you something subtle and important. Conway's surreal numbers sit at a strange intersection. They're simultaneously a number system and a game theoretic construction. The definitions are recursive in ways that strain informal reasoning. When you say surreal numbers form a field, you're making a claim about operations defined over a class so large it isn't even a set. Formalizing this forces you to confront every implicit assumption. Every clearly in the textbook becomes a lemma that demands a proof term. And the work is happening in Lean 4, which matters. Lean is open source, backed by a growing community with a mathematical library called Mathlit. That's become the largest coherent body of formalized mathematics in existence. Every theorem proved in this project can interoperate with that library. The knowledge compounds. One commenter suggests adding a wish list or project board, which is the kind of practical community building instinct that turns a solo formalization effort into infrastructure. Because that's what this really is. Not a paper, not a demonstration, a foundation that anyone can build on, extend, or correct. The proofs don't care about your credentials. They compile or they don't. Conway built the theory with pencil and paper. Now it's becoming code that verifies itself. The tools exist. The language is open. The mathematics is being liberated from the page. 8 stories deep and the hits keep coming. Let's keep building. I've spent years working on systems where the most dangerous failures weren't bugs in any single component. They were misunderstandings between teams about what the system was supposed to do. A service boundary that one team treated as a hard contract and another treated as a suggestion. Those failures don't show up in test suites. They show up in production at 3 in the morning. Armin Ronacher wrote a piece that uses the Tower of Babel as a lens for AI-assisted engineering, and the framing is precise. In the biblical story, God doesn't destroy the tower or take away the building materials. He fragments the shared language, and construction halts. Ronacher's observation is that AI agents invert this. Shared understanding among developers can erode. And construction continues anyway. Each developer has a tireless translator that can explain any corner of the codebase and make whatever local change gets requested. The code compiles, the tests pass, but the humans stop needing to talk to each other, and the architectural coherence that only comes from human coordination quietly dissolves. This is a real engineering problem, and it deserves a straight take. Run this forward 5 years. A team of 50 engineers, each paired with capable agents, shipping changes at 3 times the pace they managed before. The codebase grows. The features land. But the number of people who can explain the full system, who hold the actual mental model of how it fits together, shrinks, not because anyone failed, but because the friction that used to force knowledge transfer got optimized away. The answer is not to reintroduce artificial friction. The answer is better tooling for coordination itself. Open, inspectable system maps that update as agents modify code. Shared architectural constraints that agents enforce, not just developers remember. The same way version control solved the problem of concurrent file edits. We need coordination infrastructure that scales with agent-augmented velocity. The technology that created this problem is the same technology that can solve it. What matters is whether those coordination tools are open, visible to every engineer on the team, forkable, auditable, or whether they become another proprietary layer that only the platform vendor understands. The tower keeps rising either way. The question is whether the builders can still read the blueprints. Remember that auditable part? Well, someone put that to the test in a way you might not expect. Anytime Iveda, Robert Morris launched the first internet worm. It exploited a buffer overflow in Fingered and a debug mode in SendMail. The technical details matter less than the lesson. Every system that connects to a network eventually gets tested by someone who asks, what if I use this feature in a way nobody intended? The Morris worm didn't break any single component. It exploited the seams between components that were never designed to talk to each other. Ayush Paul just found a seam. Claude's memory system does exactly what you'd want. It builds a persistent profile so your assistant actually knows you over time. Your name, your employer, your hometown, your security questions, the stuff you confide at 2 in the morning. That profile gets injected into every conversation. Separately, Claude has web browsing tools. WebVestion makes GET requests to any URL. Each feature is defensible on its own. Together, they create something neither team probably modeled. A path from your deepest personal context straight out to the open internet, encoded in a URL path. The craft here deserves attention. Anthropic wasn't asleep. They blocked arbitrary URL navigation. Claude can only fetch URLs that appear in user messages, search results, or previously fetched pages. 3 constraints, clearly thought through. Paul's workaround was to build a page that linked to itself with a data exfiltration path, then get Claude to follow the link. The fetch was authorized because the URL appeared in fetched content. Technically compliant, completely devastating. One commenter nailed it. People run AI agents with full admin rights, no containerization, like we collectively forgot 50 years of computer security overnight. Another commenter's solution? They told Claude their name is Silly Bean. Accidentally brilliant. Poisoning your own profile is genuinely decent defense in depth. The real story is that memory systems are becoming the highest value target in personal computing. More intimate than your password manager. More comprehensive than your browser history. And right now, the architecture around them is where network security was in 1988. Functional, useful, and about to get stress tested by everyone with curiosity and a web server. The fix isn't less memory. It's better containment. Isolation between the context that knows you and the tools that touch the network. That's not a research problem. It's an engineering problem. And engineering problems get solved. Remember that supply chain security thread from earlier. Here's GitHub making the maintenance side genuinely smarter. Story 10. The strongest argument against this cooldown is obvious. 3 days solves nothing. A sophisticated supply chain attacker isn't publishing malware and hoping someone catches it over the weekend. They're compromising maintainer accounts, inserting subtle backdoors that pass code review, and waiting months before activation. A 72-hour delay against that kind of operation is a speed bump in front of a tank. And one of the commenters nails the irony. If everyone adopts cooldown simultaneously, you don't prevent the compromise. You just synchronize the blast radius. Instead of a few early adopters catching the bad version, everyone updates on day 4. Together, into the same trap. Fair points, both of them. And both miss what actually matters here. The cooldown isn't a security boundary, it's cultural default. And defaults are the most powerful force in software. Most developers never touch their Dependabot.yml. Most teams merge the green checkmark without reading the diff. GitHub knows this, which is why they made it opt-out instead of opt-in. The 3 days catches the dumb attacks, the typo squats, the accidental publish of a broken build, the attacks that account for the vast majority of actual incidents. One commenter points out that distribution package managers solved this in the 90s. Stage rollouts, maintainer review, holding periods. They're right, and the deadpan delivery writes itself. We spent 2 decades telling everyone to npm install their way to production, mass centralizing trust in a registry with essentially no gatekeeping. And now we're slowly, painfully rediscovering that maybe the Debian maintainers weren't just being difficult. The tools to verify dependencies exist. Lock files, reproducible builds, signature verification. The cooldown buys time for people to actually use them. This has been your daily tech feed for Hacker News for July 15th, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7, voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth documenting. We'll see you back here tomorrow.